Welcome you all to the live session 10 of the course Manufacturing Process and Technology 1 and 2. So in this session we will try to solve some practice assignment problems based on the uh, process electrochemical machining. So let's get started with the first problem. So this is the first problem. So first of all, please take some time and try it by yourself. After that we will discuss it together. Okay, let's try to solve it together. Okay, so in, in the problem, what has been asked, electrode double layer is generated in which case? So as we know, in here we are, yes, Nagasrinivas, can you please try it by yourself first of all, then we will discuss it together. You can give your response in the chat box. Yes, correct. So here we are talking about the electrochemical machining process. So in electrochemical machining process, we we have a tool and we have the workpiece, and everything is dipped in electrolyte. So and workpiece is connected to the positive charge and tool is connected to the negative terminal of the battery. So basically tool and workpiece are nothing, they are acting as an electrode. They are electrode. So it is very similar to electrolysis process, but here uh, our aim is to machine the workpiece. Machining means removal of material. So here the material removal has been taken from the workpiece and going it is the material from the workpiece is going to get dissolved in the electrolyte. So the blue one, this is the electrolyte. So tool and workpiece, they are separated by electrolyte. Electrolytes are, they are nothing but they are charge carrier or ions. They are having the ions to facilitate the flow of electricity. And what happens here? Here the material dissolves from the workpiece to the electrolyte and it gets precipitated. So because of this, potential difference which we are applying. And this is the fundamental concept which is involved in the material removal. So that's why it is called electrochemical machining process. And the tool and workpiece, they are acting as a electrode. And let's try to see a little bit more about the electrode. So here this the blue one, it is a electrode. So basically what we are trying to see, what happens when electrode comes in the contact of electrolyte. So I am telling, yes, material is dissolving from the workpiece to the electrolyte, but how it, what happens at the interface, those things has been shown here. So the most left side of this diagram, it is showing a electrode which is having positive charge. But in electrolyte, we are having both kind of charges. So positive, these are positive ions, so these are negative ions, these are positive ions. So electrolyte consists both types of ions. So this is the interface which I am showing. So we have electrode which is carrying positive charge. It is dipped into electrolyte, and electrolyte have both kind of ions, positive and negative. Since so the very first layer which we see here, we can see this green one. So these are the mostly the a very thin layer of H2O or the water molecules. The very first layer which is coming just after the electrode, that is the thin layer of water. So that is called solvation layer. And just after this, to balance this positive charge, the negative ions, they will start accumulating just after the solvation layer. So these are the negative charges which are getting accumulated. So the well, if we draw a center line from the very first, if we draw the center line of first layer of the negative charge, that is called the Helmholtz layer or Helmholtz plane. And after this, after the Helmholtz plane, or after the first layer of the negative ions, there are other negative ions. They are present behind the Helmholtz plane. Okay, so what we can see, there is a positive charge layer, and after that we have a layer of ions which is negative in charge. That is already we have told, that is called Helmholtz plane. And after that we have some ions, they are diffused. They are negative ions but they are diffused. That is called the diffuse layer. Okay, so overall if we see, we will see, if we see in this region between these two planes, if we see, there is a layer of positive charge, and after that there is a layer of negative charge, and that is called the double layer. So that is the question. So double layer is nothing. It is a layer of two different types of charges. It may be ion, and it may, so here we can see we have positive charge on the electrode and negative charge on the ions. Opposite can also be true. If our electrode is negative charge, then positive charge will get accumulate nearby region. So this is called double layer, and this will happen only when electrode will dip inside the electrolyte. So the correct answer is B. Okay, let's move to the next problem. Please read the problem and first of all try it by yourself. After that, we will discuss it together. Okay, so what has been asked in the problem? Which of the following which of the following is not true corresponding to volume removal rate in electrochemical machining? So these are the options. It is directly proportional to the density of a node. It is directly proportional to the current. It is inversely proportional to the valency of cations, or all statements are true. So again, if you see, this is the again schematic of the electrochemical machining. So so here we can see the workpiece is connected to the positive terminal, and tool, this is the tool is connected to the negative potential, and in between there is a flow of electrolyte. We are providing a flow of electrolyte. So material removal will take place from the workpiece region. So in this region, material removal will keep on taking place, because this is the region where the positive and negative, this electrode is, if you see, this is the insulated layer. Okay, so here the sidewise no machining will take place, only from the bottom machining will take place, because here the tool is exposed to directly to the workpiece, and there is a layer of electrolyte. So this is the very similar process to the this is very same as the process of electrolysis. So material removal is governed by basically Faraday's law. So here I will quickly try to write down what is the Faraday's law. So MRR in ECM process is governed by following laws of Faraday. So basically he has proposed two laws. First one was The amount of material dissolved or deposited is proportional to the quantity of electricity passed. And second law was the amount of material deposited or dissolved by the same quantity of electricity is proportional to their chemical equivalent weight. Chemical equivalent weight. If we want to write in the terms of formula, then what we can say, the mass which is deposited is directly proportional to the current, and for how long current is being passed, as well as to something called equivalent weight. So what is epsilon? It is nothing but gram equivalent weight. Okay, so it is nothing but atomic weight divided by valency of the material, and mass is weight in grams. And current I is in amperes. Okay, and time t is in second. So now if we try to see what has been there, so first option is it is directly proportional to the density of the anode. So we have seen that there are only two things on which material removal rate depends. First is the how much electricity we are passing for how much time, and another thing is there the gram equivalent weight of the material or the workpiece. So density is not coming into the picture, so first this is not correct. And it is directly proportional to the current. Yes, it is correct. It is inversely proportional to the valency of cations. Yes, because already I told the MRR or M is directly proportional to epsilon. Epsilon is nothing but atomic weight by valency. So what we can say, M is inversely proportional to the valency. So this is also correct. So it is, so these two statements are correct. The only statement, so statement A, it is not correct. So since all the above statements are not correct, this is also an incorrect statement. Okay, so only correct statement are B and C, other two are the not correct. So is it clear? Okay, so if it is clear, let's move to the next problem. If you have any doubt, please ask me. Okay, otherwise we will move to the next problem. Okay, let's move to the next problem. Please read the problem and try to find out its answer first of all by yourself, then we will discuss it together. You can give your response in the chat box. First of all, please try this problem by yourself. After that, I will discuss the solution. Okay, so I I have got response from Naga Srinivas. So shall I start discussing the solution, or you need some time? Okay, so so I'm starting discuss the solution. If you have any doubt, please let me know. Okay, so here let's try to understand what has been asked in the problem. Determine the current required for machining iron. Atomic weight is given, valence is given, density is given for achieving volume removal rate of 15 centimeter cube per minute. So what we have to find out? We have to find out the current. And what we know the material is iron and its atomic weight is atomic weight. Now we will call the atomic weight by A. It is 55.85 gram and its valency is 3. So that let's use the letter Z for the valency. So that is 3. And for density, let's use the symbol rho. That is 7.86 gram per centimeter cube. And volume removal rate Q. which is it is given 15 centimeter cube per minute. So what is unknown? Current. And if you remember, the what is the relationship between the volume removal rate and given parameters? So that is nothing but Q is equals to AI, that is atomic weight, times current divided by density into valency, and there is a constant that is called Faraday's constant. Okay, so we just need to substitute the values in this equation. So Q is given in centimeter cube per minute. So we need to change it into SI units, or we have to use it in centimeter cube in per seconds. So Q is 15 centimeter cube per minute, and if we convert it into the centimeter cube per second, then it will be equals to 15 centimeter cube by 60 centimeter cube per second. So let's substitute everything here. A is 55.85 and current that we need to find out, and rho is given 7.86 and Z is 3. F is constant 96,500. So if we solve for I, we will get 10185.6 amperes. So which option is this? It is D. So correct option is D. Is it clear? The You can see the current value is very high. It is 10,185 amperes. So this is very high current. So yes, that is true. In electrochemical machining, voltage value we keep lower, but current value is very high. Okay, so correct answer is D. Any confusion? Okay, so let's move to the next problem. Please read the problem and take some time to calculate it by yourself. After that, I will discuss uh, I will discuss the solution. Okay. Whether problem is clear what has been asked, or there is some confusion in the question itself? Okay, please take your time. Okay, please take your time and let me know. Yes, correct. Okay, so let's try to solve it together. So first of all, let's try to understand what has been given in the problem. The composition of mnemonic alloy that is used for the turbine blade is 18% cobalt, 62% nickel, 20% chromium. It is being machined electrochemically with, we can see the current value is very high, 1500 amperes. Find out the volume removal rate, that we need to find out. And what else is given? The dissolution valency of chromium is 6, whereas for nickel and cobalt it is 2. Additional data what is given there, the gram atomic weights of cobalt, nickel, chromium. So that has been given here, as well as densities for all three elements are given here. Okay, so now let's list it down what things are given. First of all, so we have alloy which has these three elements: cobalt, nickel, and chromium. So first of all, their composition is given. So that is 18% of cobalt, 62% of nickel, and 20% of chromium. And what else is given? The valency of each element is given, that is Z. For cobalt it is given 6, whereas for nickel and chromium it is given 2. As well as atomic weight of each element is given. Not atomic weight, it is the directly they have given equivalent weight. Gram atomic weight, okay. Gram atomic weight. So we will note down all the gram atomic weight, that is 58.93 and 58.71 and 51.99. And what else is given? Density rho is given. So that is 8.85, 8.9 and 7.19. So first of all, what we have to do, we have to find out the average density of the alloy, because that will be needed to calculate the metal removal rate. So for the case of alloy, first of all, let's write down what is the equation for the material removal rate. So Q is the MRR. It is given by 0.1035 to 10 to the power minus 2 divided by average density of the alloy times 1 divided by summation of composition. Xi is nothing but composition, okay, into Zi into valency upon atomic weight. So this is the relation from which we can find out the material removal rate for the given alloy. Also, what has been given? Current I value is given amperes. So this is the MRR per unit charge. Okay, this MRR which we will get, that is for the per unit current. Okay, so whatever MRR we will get from this equation, we have to multiply it by current value, then we will get the actual MRR. So first of all, we need to find out average density. So average density, what is the average density? It is given by 100 divided by summation of from I to n xi upon rho I. Okay, if we will substitute the values, what we will get? 100 divided by 18 divided by 8.85 plus 62 divided by 8.9 plus 20 divided by 7.19, and if you calculate it, what we'll get? 8.4876 gram per centimeter cube. So that is the average density of the alloy. So now we will substitute the average density in MRR formula, and we try to calculate material removal rate per unit current. So now we will write Q is equals to divided by average density is nothing but 8.4876. Now we will substitute all other values. So what all other values are? That is composition, summation of composition into valency upon atomic weight. So this is for cobalt, and here this is for nickel, and lastly it is for chromium. And after solving this value, what we will get? 2.4377 into 10 to the power minus 5 centimeter cube per second per unit current, that is ampere. So right now, what is the current value we have? That is 1500 ampere. So Q 1500 ampere will be into 1500 and this value we will get it centimeter cube per second. So that is nothing but 0.0363 centimeter cube per second. Okay, so which option is this? Yes, C. The correct answer is C. So let's move to the next problem. Yes, please read the problem and you can give your response in the chat box. Okay, yes, you are correct. So what has been asked in the problem? What are the various types of over voltages in electrochemical machining? So what is the over voltage? So it over voltage is nothing. Over voltage, it is the extra potential which must be applied between the electrodes, which must be applied to electrode to initiate the electrode reaction, initiate the electrode reaction in an electrolytic cell. So, so in electrochemical machining, we are trying to remove the material by electrochemical reactions. For that, we are providing some voltage by some external source like battery. But whatever potential that we actually needed for to carrying out the reaction, we need to supply little bit more than that, and that is called the over potential. So there are many types of over potential. So here I will show that this is the distance between two electrodes. Okay, and this is the, on the y-axis I am showing voltage, and on x-axis I am showing distance between electrode. So here I am assuming anode, here it is cathode. So if you see in actual experimental setup, so we are we will get some, the potential curves will look something like this. So first of all, there is a potential here this is the anodic region. So first of all, the potential drop which we see, that is called the anode potential, and after that there is another over voltage is there, that is called activation polarization over voltage. And after this there is something called ohmic voltage, ohmic over voltage. And there is another over voltage, that is called the concentration polarization over voltage. So these are all the regions of the double layer. So these are these four voltages which I have shown here. So that is it, that drops takes place in the vicinity of the interface of anode and electrolyte. So there is we know there is a formation of double layer takes place, and within the double layer these all drops will takes place. So this drop takes place in the anodic region. So that is called the anode over voltage. And similar, exactly same type of drops also takes place at the cathode, and that is called cathode over voltage. And this region, this is straight line, that is the region of electrolyte. So this here we can say, we can see this is the region of electrolyte. So in electrolyte, Ohm's laws is followed. That's why we can see there is a linear curve. So this is called ohmic voltage drop. So after that, same thing will happen to the cathode also. So here we can see, first of all we have anodic potential drop, then we have activation polarization over voltage. So it is nothing but it is kind of activation, uh, activation we need to keep some additional potential in order to facilitate the movement of ions, and that is involved. A little bit of polarization has to be done in order to initiate the mo- initiate the motion to the ions, and that is called the polarization over voltage. And ohmic over voltage is nothing but there is a some thin solid layer around the electrode. So whatever drops takes place there, that is called the ohmic over voltage. And concentration polarization over voltage, that takes place in the diffused region of the double layer, because we know electrode have some charge, and around it the opposite charge ions are accumulated, and because of that, in order to in order to facilitate the motion of ions, we need to provide additional voltage. So the additional voltage which we provide to 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 move the ions, where they are concentrated. So that voltage is called concentration polarization over voltage. So these are the type of over voltages which we can see in during the electrochemical machining process. So the correct answer is activation, ohmic, and concentration gradient. Yes. So correct answer is C. Okay. So we will move to the next problem. Please read the problem and you can give your response in the chat box. Okay. So so let's try to see it together. So what has been asked there? Which of the following is true about electrochemical machining process? So first of all, uh, let's quickly draw this rough diagram. So tool, workpiece, and electrolyte. Tool is connected to the negative charge, workpiece is connected to the positive charge, and there is a electrolyte. So material removal has been taking place from the workpiece because we have applied some potential difference, and because of this, between the tool and workpiece we have applied some potential difference, and because of which there is generation of electric field. And here we have electrolyte where we have some positive ions and we have some negative ions. And what is happening here, the ions, because of this electric field, the ions are moving in opposite direction. Tool is negative, so positive ions will come, they will get collected over here, and negative ions will come, they will get collected over near the workpiece. So, and because of this applied potential, there will be a reaction which will takes place between the negative ion as well as the workpiece material. So here the material removal has been taking place because of the electrolytic reaction process. Okay, so if potential which we have applied is sufficient enough, and the current which will be generated in this fusion, and we have appropriate electrolyte, then what will happen? The ions will come and they will react with the workpiece material, and they will get precipitated, and we will flush out the precipitates. So that we do. And here the material removal is been taking place because of the electrolytic reaction. So that is the main responsible, that is the mainly responsible for the material removal. So therefore first option which we see, high strength material. So as long as workpiece is electrically conductive, then we can definitely machine it by electrochemical machining process. So whether whether material is iron, aluminum, copper, or magnesium, whatever material we will take, we can see iron has higher strength, aluminum has low strength, copper has medium strength. So although each material have different strength, but since they are conductive, they are conductor, and if we use appropriate electrolyte, then these all these materials can be machined. So from electrochemical process, we can machine any material as long as material is conductor in nature. So strength is not going to play any role in electrochemical machining. So this is wrong. So next is the excessive tool wear. So in what we do in electrochemical machining, our aim is to remove the material from the workpiece by doing some reaction between electrolyte and workpiece and making a precipitate and flush it out and remove it. So that is the mechanism. So here material removal has been taking place at the atomic level. So atom by atom material is getting removed from the workpiece, and the interaction which is happening, that is between the workpiece and the electrolyte. Here we are not having any kind of physical contact between the tool and the workpiece. Therefore tool will not get deformed or it will not get machined at all. So tool wear is not a problem of the electrochemical machining. Job of the tool is it should have counter shape. Whatever shape, it should have the same shape which we want to machine on the workpiece. So tool shape is going to determine what shape, in what shape machining would takes place on the workpiece. And also another job of tool is to it should be it should be conductive, so that when we connect it from the battery, the negative charge would appear over the tool, then only electric field will establish. So here, because there is no physical contact between the tool and workpiece is taking place, therefore damage to the tool will not at all happen. So tool wear is not takes place. And C option is it gives burr free surface. Yes, it is correct. So if you are aware what is the burr is nothing, it is the unwanted projections which are left out after the machining process. It is very common in conventional machining. Suppose if I will take the example of the drilling. So suppose we have a plate. If you want to drill it from conventional drill bit, okay, what we do? We give some we give rotational motion to the drilling tool and we will apply a force perpendicular to the workpiece, and material removal will takes place from the workpiece, and this material removal will take place by by the physical contact between tool and the workpiece. And after drilling, you can find on the back side of blade some material will remain, some small chunk of material will remain stick, or they are left out as a projected materials. So that is called the burr. So here this burr has been produced because there was there because here material removal was taking place by the physical contact of the workpiece and the tool. And since here in the electrochemical machining there is no physical contact between the tool and workpiece, therefore formation of burr will not take place at all. And here the material removal is taking place atom by atom. So there is no chance of leaving any projection of chunk of material over the workpiece. So we will get very neat and clean surface after electrochemical machining. So yes, this is true. It keeps burr free surface. It is correct. And option D, surface hardness of workpiece gets reduced. No, this is wrong, because here the mechanism is on the surface we have some atoms, and when we apply some voltage over here, the atoms basically they acquired some charge, and when some opposite kind of opposite opposite charge ion comes from the electrolyte, and if it reacts with these positive atoms, then because of reaction some precipitate will form, and because of this material removal has been taking place. So whatever has been happening, it is because of the electrochemical reaction between the surface atom of the electrode and the electrolyte, whereas the atoms which are in the second layer, they are not get affected from the material removal process at all. So no hardening will takes place. Whereas if you talk about in the conventional machining process, suppose we are trying to remove material from cutting tool, carbide tool. So suppose this is the first layer of the atoms. What we are doing here, we are moving the tool over the over the sur or the by giving some depth to the workpiece, and we are removing the material by plastic deformation. What is the plastic deformation? That is the permanent displacement of atomic position, and because of which after removing the material we are disturbing the surface which is which we are getting after machining, and that that deformation we are doing plastically. And therefore in conventional machining process, after removing the material we definitely get some some hardening, or if we have generated lots of heat, then softening can also takes place. So hardening hardness property of surface that can be changed in conventional machining process. But in if we talk about particularly electrochemical machining, the hardness will not get changed at all, because here the atom by atom removal has been taking place without disturbing other atoms. So no changes hardness. Hardness value will not change after machining. So only correct option is C. Okay, is it clear? Okay, you can ask me if there is some doubt. Otherwise, we will move to the next problem. Okay, we will move to the next problem. Please read the problem and give the correct answer for this. Uh, Find out the correct option. You can give your response in the chat box. Whether problem is clear to you? The problem is clear or not? What has been asked? Okay, you can keep your response in the chat box. After that, we will discuss it together. Okay. If there is some confusion in the understanding the problem, you can ask me. Okay, let me help you out. So here, if the feed is 0 in ECM, the gap y. Here we have to fill, this is the fill in the blanks which we have to fill out, and there are something which is given where y0, lambda and t are the initial gap, process constant calculated through the various parameters, and time respectively. So we need to fill the correct word. So first of all, I will draw some schematics and then I will explain. So suppose we are having a tool for the electrochemical process, and we have a workpiece. And there is some gap in between the tool and the workpiece that we are denoting it by y. So here y-axis is showing the gap between the tool and the workpiece, and this is the x direction. In between the tool and workpiece there is a flow of electrolyte taking place. So blue one, I am showing that this is the direction of electrolyte. So there is a flow of electrolyte which has been taking place between the tool and the workpiece. And what we are doing, we are connecting tool to the negative charge, negative potential, and workpiece to the positive potential. So as soon as we will apply a voltage across the tool and the workpiece, the material removal will takes place because of the electrochemical dissolution of the workpiece. So if workpiece will starts getting machined, or workpiece starts getting dissolved in the electrolyte, then what will happen? That there will be change in gap will takes place between the tool and the workpiece. So that we are denoting it by, so rate of change of gap between tool and workpiece. This is given by dy by dt, and this rate of change of gap between the tool and electrode, this has been find this has been found to following this relation. So this equation you can go and find out in the video lectures of the course. So this is the governing equation that defines the rate of change of gap between the tool and the workpiece, where lambda is a constant, process constant. So this lambda is a constant for given electrode and electrolyte material. Material combination. For given operating voltage. And F is the feed which is given to the workpiece. So F is the feed. This is the feed velocity which sometimes we give to the workpiece. Okay, so this is the main equation, and now we solve this equation for different conditions. So out of those conditions, one of the condition is if the feed is 0. So feed which is given here, this value is 0. If F is equals to 0, then what we are left out with? We can write for 0 feed. If F is equal to 0, then we will get dy by dt is equals to lambda by y. And if we integrate it, then what we will get? We will get y square is equals to y0 square plus 2 lambda t. So after integrating this equation, we will get this, where y0 is the initial electrode gap. Y0 is nothing, it is the initial electrode gap, or this is the initial gap between the tool and the workpiece. Or we can say at time t is equal to 0, y was y0. So after putting this boundary condition, the relation which we get between the gap as a function of time, that is y square is equals to y0 square plus 2 times lambda t. Okay, I need some more space. Okay, so the what we got this equation. So this is the relation between the gap between the workpiece and tool at some time t. And now if we take a square root to the both side, then we will get this. So this is the function of time. So other things are constant. So this is the rate, this is the gap which we will get at between that workpiece and tool at some time t. And if we plot it, it will look something like this. Y as a function of time, which is the gap between the workpiece and tool, and on x-axis we are plotting time. So we will get an increasing function, something like this. And what is this? This is the initial electrode gap. So we can see this is continuously increasing as a parabola. So because this is the equation of the parabola. So the correct option is Okay, here. So if we see here, what's the this is the final relationship we have got. So which one is the similar to this? So yes, this one, and nature of function is increasing. So gap will keep on increasing and it will follow this relationship. So correct answer is D. Okay, is it clear or there is some confusion? Okay, okay, we will move to the next problem. Please read the problem and try, first of all, try it by yourself. Then we will discuss it together. Okay, okay, yes, correct. So we will uh, let's try to see what has been asked in the question. Which of the following statement is most appropriate for the equilibrium gap? So as I told, let's quickly draw the diagram which I have drawn in the earlier problem. So here we have some tool and here we have some workpiece. So here this is the tool, it is the workpiece, and in between there is some electrolyte, it is flowing, and there is some gap that we are calling y. So here y-axis is showing the gap between the tool and the workpiece, and x-axis it is showing the direction of electrolyte flow. So as soon as we apply some voltage on the tool and the workpiece, so material removal will start taking place over the workpiece. And already we know that we have a relationship which is something like this: dy by dt is equals to lambda by y minus f. So suppose already I have shown you, when we are not giving any feed to the workpiece, then what was happening? The material was getting removed. So material was getting removed slowly, 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 and this gap was increasing as time time was passing on. So he as time keep on passing, this gap will keep on increasing. But if you see this curve, after some time, what you will see, the rate of increase is almost negligible. So here, so basically after some time you won't see any visible change in gap. So Suppose after removing this much of material, the strength of electric field between these two, between this the tool and the workpiece, it will not remain. The strength of electric field should will keep on decreasing as the since voltage is constant. If we keep on increasing the distance between these two electrodes, then strength of electric field will keep on decreasing, and a time will come when the reaction between the electrolyte and workpiece will not take place because of insufficient field strength. So after that time, the material removal will almost negligible. Okay, but what we are looking for, we want to remove more material. Then what we have to do, we have to keep on moving the workpiece towards the tool so that material removal will keep on taking place continuously. So if it is needed, then we keep on giving some constant feed motion to the workpiece towards the tool so that material removal process should not get stopped. Okay, so that is called the constant gap condition. Earlier, which I have shown in the previous problem, that was the zero feed condition. So this is the main equation. In earlier case, we put feed equals to 0, but now this is the another condition. Here we are giving some feed to the workpiece, but that feed which we are giving to the workpiece, it is not random one. Here we want to give that much of feed to the workpiece so that whatever material is getting removed, that this gap should not get changed. So at what rate this gap is decreasing, for same rate if we give feed to the workpiece, then this gap will become constant. Okay, in that case this y will become equilibrium value of y. So that is called, that constant value is called y equilibrium, because we are providing same feed to the workpiece by which material removal, by which the gap is decreasing because of the material removal. That gap is called equilibrium gap. So this term ye. Now let's solve this equation for that condition. So if we are telling this gap is not changing, that means dy by dt will become 0. So if this will become 0, what we will get? If we substitute 0 in this equation, we will get 0 equals to lambda by y minus f, or what we can say, f is equal to nothing but lambda by y. So here the y which we will get, that is nothing but equilibrium. Okay, or we can say ye is equals to lambda by f. So this is the equilibrium gap, and that is equals to this constant by feet. So let's try to see what are the correct options. First one is, it is inversely proportional to feet. Yes, equilibrium gap is inversely proportional to feed. It is correct. Now it is calculated through the no gap change condition. Yes, we have put dy by dt is equals to 0, and C option is it is corresponding to a constant feed case. Yes, this feed value which we are giving, it is constant and it is same as the it is same this feed is constant, so that this feed this feed should be equals to the rate of material dissolution, so that dy by dt, at what rate this is changing, we are giving same feed value, and that is the constant for given set of electrolyte and electrode combination and for given set of voltage. Okay, so this statement is also correct. Since all three are correct, correct option is D. Okay, so any confusion? Okay, so if there is no confusion, let's move to the next problem. Please read the problem and you can give your response in the chat box. Yes, you have given correct answer. So uh, again, we will quickly draw the schematic. It is a tool, and here we have workpiece, and we are connecting tool with a negative charge and negative potential, and workpiece to the positive potential, and in between there is a flow of electrolyte which is taking place. Always I am using flow of electrolyte. This electrolyte which we are giving, it is flowing, it is not constant, it is not stable, it is flowing. So why this flow is required? So already we know what has been happening when we apply potential. Because of electrochemical reaction, the workpiece is getting reacted to the electrolyte. The atoms of the workpiece is reacting to the ions ions of the electrolyte, and they are forming some precipitates. Okay, so so one task of this flow is to wash away whatever precipitates are forming. Okay, so that is B option, to remove precipitates. And other other task of this flow is to avoid any type of ion concentration, because if ion concentration will not be uniform, the material removal will not take place uniformly. Somewhere more material will be removed, and somewhere less material will be removed. So in order to avoid any kind of uh, concentration of ion, we keep on flowing the electrolyte so that we could get uniform ion concentration throughout the gap between the tool and the workpiece. So that is also correct. As well as, because of the chemical reactions, the temperature of electrolyte will keep on increasing, and if we flush away and we keep on supplying fresh electrolyte, the temperature between the tool and the workpiece region, it will be constant. So we don't want overheating of the electrolyte. So if we keep on supplying fresh electrolyte, then the overheating problem can be avoided. So since all three are correct, the correct option is D. I think there should not be any confusion in this problem. So let's move to the last problem of the day. Please read the problem. First of all, please try it by yourself. After that, we will discuss it together. Okay. Okay. So let me help you out. So the height of peaks of surface irregularities of two electrodes with flat surfaces are 7 microns and 10 microns. The workpiece is pure iron. Atomic weight is given, valency is given, density is given. Applied with a voltage of 15 volts, and we have to find out highest possible feed rate which can be used. And here we have given conductivity as well as the over voltage values. So, uh, so if you see the tool and workpiece surface, so they are not flat at the atomic level. So again there will be some roughness to the tool and the workpiece. So just for the schematic I will draw something like this. Okay, suppose this is the tool. This is just exaggerated view. So there is the similarly there will be a workpiece something like this. Tool is connected to the negative potential and workpiece is connected to the positive potential, and in between electrolyte will keep on flowing. So what has been first of all, the height of the peak of surface irregularities with for two electrode is given 7 micron and 10 microns. So what it mean? It means this value, the okay. So this is the mean line, the dotted one, and this is the peak value. So that is the height of valley or the peak which is given, that is 7 micron. Here it is 10 microns. So what has been asked, what is the estimate the highest possible feed rate which can be used. So what is, in order to do machining process between the tool and the workpiece, what we have to do, we have to flow some electrolyte in between them. So what is the minimum electrode gap which we can think of, so that there should not be direct contact between the tool and the workpiece? So that will be the condition when this gap will become closer to the zero. So just before just when the contact is avoided, in that case what will happen? If we see the gap between these main lines, that will be becomes sum of these two, that will be about 17 micrometer. So uh, what we can write, the equilibrium gap is nothing but 0.0017 centimeter, in order to avoid direct contact between the tool and the workpiece. And for that feed rate, what is the feed which we can give for this condition? So that there is a relationship. Feed is nothing but Ka, sorry, this is okay. You have seen there is something like that. This equation is looking something like that. Okay, feed is equal to lambda by equilibrium gap. So this feed will be become maximum when this will become minimum. So minimum will be possible only if we bring them so closer, so that direct contact between tool and workpiece can be avoided. Okay, so therefore this relationship, we will use this relationship in order to find out the maximum possible feed. So what is here? Let's note down here. In this relation, K is nothing but conductivity of electrolyte, which is given 0.25 ohm inverse centimeter inverse. A is atomic weight, that is 55.85 gram. Voltage is 15 volts, so V is given 15 volts. And there is over potential that is given by delta V, that is 1.5 volts. So although our battery is providing 15 volt, but the actual voltage which we will get between the electrolyte, that will be something this 15 minus over voltage value, that will be the actual voltage which will be available for the machining. Okay, and what else is given? Density is 7.86 gram per centimeter cube, and valency is 3, and Faraday's constant is 96,500. So now I think we have all the values, and now we will substitute everything in this equation. So F max we will get is 0.25 into 55.88 into 15 minus 1.5 divided by 7.86 into 3 into Faraday's constant into maximum minimum equilibrium cap, and if we calculate it, what we will get, F max is equal to 0.048 centimeter per seconds. Okay, so correct answer is B. Okay, is it clear? Okay, so this was all for the today. So we will end this session here, and we will meet next week at the same timing on the same day. Okay. Okay, thank you all. Yes, you can leave the meeting.